Sweet. So we're gonna quickly finish off the physics with electricity and electrostatics, and then jump to chemistry. Okay. By show of hands, who's like perfectly okay with electricity and electrostatics? Like, okay, who's like I can get a 60 if I try. Okay, that's good. Sweet. So now, if you guys turn your books to page 15, we can see our summary of electricity there. Okay. Now I'm going to just bomb through this quite quickly for the sake of time. So everyone knows the one important one, Ohm's law, right? So if you look at the Ohm's law triangle, D at the top, I and R. Yes? Okay. So I've got any sort of electrical circuit. Let's say I've got like a resistor here. R1. Can you guys the back see? Okay. You can have an ammeter there. You have a parallel bit of resistance here. Another resistor here. Okay. So this will be R2 and this will be R3. Okay. So the key things to remember with electric circuits, right, is very important. The one equation you always have to sort of know and touch through, Ohm's law, right? Your R is equal to V over I. I like that. If we go back to grade 7, we have Q is equal to I times T. So with that, again, Q is our charge, right? I is our current, T is the time. So that if you want to see what charge flows, you're going to look at the current and how long the current flows. That'll tell you how much charge went through a particular point. R is equal to V over I, that's our Ohm's law, where our resistance, right, in a component is equal to the potential difference across that component divided by the current. One thing, just a few things I want you guys to remember. When we deal with current, in a current act in series versus in parallel. And in series? Same. Okay. So current splits in parallel and it's the same in series. So if I look through here, the current coming out there, going through here, is the same current, gets to the junction, splits up, right? In the ratio of my resistors. Meaning the biggest current goes to the smallest resistor, the smallest current goes to the biggest resistor. Then goes through there, comes back together, then it's the same current that I had before anyway. And it continues, the same current comes back there, and then continues again. That makes sense. So think of current as you trying to get from one place to another early in the morning during sort of rush hour time. You get to the one junction, and the road sort of you use, that road there has got tons of traffic, and you're like, actually I'm not going to go that way. I'm going to go the one that's got least traffic. That's what current does. Gets to a junction, always picks the route of least resistance. So if I had to have a cable going from here till there, when the current gets to just after R4, it goes, well, there's resistors that way, and there's nothing that way. And then it's going to basically skip that entire part of my circuit and all go through there. Because there's no resistance, there's no traffic through that circuit there. And then continue and then basically short circuit that whole part there. Yes? Okay. How does my voltage work in series and in parallel? Anyone? Yes, so it splits in series and it's constant in parallel. So as, let's say, my current leaves here with a certain amount of energy and potential, it goes through there, and then some of my voltage sort of drops there, comes across there, it drops there, goes there, drops there, and comes back empty. So the example I like making is think of your battery, your cell, right, as a bakery. So that's a bakery. All your components in the circuit are like little shops. Okay? So now, if I've got a 12-volt battery, right? So imagine that as me leaving my bakery with 12 loaves of bread. It's a business, I want to be as efficient as possible. I'm not going to leave with 14 loaves of bread when people only ordered 12 loaves of bread. That makes sense. So I leave you with 12 loaves of bread. go there, go there, go there, go there. And then as I check in, the guy at the door says, well, hey, how many loaves do you have? I'm like, I still got 12. He takes whatever he takes out. On the way out, I check, I've got 10 loaves left. Now, the whole where potential difference comes in is now we look at the value before and the value after. And then you say, well, hey, they're on the walkie-talkie, the guy on the outside saying, listen, how many did they come in with? 12 and left with 10. Let's work out how many loaves they left inside. They left 2 loaves inside. Therefore, this here would have 2 loaves, basically. We'd use 2 volts of our energy from the battery. That makes sense? And the potential. So I've got 10 left, and I'm going to go this way. And then imagine your resistance now, parallel resistance, as like a little shopping center, where they're going to drop it off at the receiving, not go to all the individual shops. So they're just going to come here, and they're going to come in with 10, drop off a certain number. You see there's a lot of guys that live here, and then they come out with 6. Then if you put a voltmeter around here, the guys sort of call again, hey listen, they came in with 10, how many did they leave with? Left with 6, okay, that's fine. That means they dropped off 4 in there. And then you come. This is the last stop. I have to drop everything else there. So I've got 6 going this way. If I have 6 coming in there, I have to leave with nothing because I have to get here with nothing. Does that make sense? So then I drop off 6. My potential difference across here is going to be 6 volts. Come there with nothing. And then as I get to the bakery the next day, I get 12 more and I do the runs again. So you leave here with 12. That's why when you check your potential difference across your battery, it will tell you how much energy you have in the entire battery. That you will always leave with 12 and you'll come back with nothing. Does that make sense? Okay, sweet. So then, to get every other value, like your current and anything like that, we're going to use our Ohm's law to get to the answers we're looking for. And internal resistance, how does that now affect my entire system? Anyone with a hand quickly?
The voltage gets used up inside the actual battery.
Yeah, okay. Exactly. So now, imagine you've got 12 volts that you produce, but now your driver comes in the morning and he's got to have breakfast before he leaves. So he has maybe half a loaf of bread at the shop before he even delivers anything. So he comes in there, he loads everything on, thinks, oh, I'm so hungry, I didn't have breakfast this morning, pops open a loaf and just grabs half a bite or a few bites of half a loaf, puts it back and then delivers now 11.5 loaves, basically, at the end of the day. And if he doesn't take that, he won't have energy to keep on going for the rest of the day. Okay, so your internal resistance, basically, is what uses up some of your current and some of your energy in the circuit here before you leave out. That makes sense? Okay, so then in that case, you're going to just modify our equation. So we're going to go from V is equal to IR. That's when we discount internal resistance. And when we now include internal resistance, we realize that our V becomes the EMF of my cell, my current remains current, and my total resistance becomes the R external for the entire circuit plus my R internal. Yes? Yeah. And you apply this the exact very same way that you'd apply your normal Ohm's law, just that now you're dealing with this resistance and that resistance there. Is that okay?
Yes.
Yeah, sure.
Yeah.
Okay. Quickly touching base on electrostatics, think back to when now we did Newton's law of gravitation. That was about an attractive force between 2 objects with mass. Okay, electrostatics is very similar, except in this case it's about a force of either attraction or repulsion between 2 objects with a charge. So if I've got charged object Q1 and charged object Q2 there, they will experience an electrostatic force due to the charges that they each have. So if you have them both being positive, they will repel each other. If one is positive and one is negative, they will attract. And if they're both negative, they will repel. Like charges repel, opposite charges attract. Yes? Okay, cool. And then the equation that we have there is going to simply be, my F electrostatic is going to be K, my constant, times Q1 times Q2 divided by R squared. Okay? And remember, the force that this exerts on that one is the same force that Q2 exerts on Q1. Yes? Okay. And then quickly, then if we're going to look at one charge and look at the electric field strength around my object, E is simply now equal to K times Q divided by R squared. Last important thing for electrostatics is when they interact. If you have 2 charges that come together and separate, what happens?
They give equal charges?
Yeah, they share the charges equally amongst each other. So now, in this case, you'll say F nu when they touch is going to be F1, sorry, not F, Q nu. So the new charge will be Q1's old charge plus Q2's old charge divided by 2. So if one object comes with 2 coulombs of charge, other one comes with negative 2 coulombs of charge, you can say 2 plus, let's say negative 2 for the other one. Negative 2, which will give us 0, and they'll move off neutral. And if one was 2 and the other one was negative 4, you'd have 2 plus a negative 4 giving you negative 2. Split that in half, they'll each move off with a negative 1 charge of coulomb. Coulomb charge. Coulomb of charge. There we go. Does that make sense?
Yeah.
You guys with me?
Yeah.
Any questions? Yes? So you're asking if, does it make a difference if, let's say I've got 1 coulomb and the other one is negative 3 coulombs. If I drop the negative and say 1 plus 3 divided by 2, yes, it will make a difference. Because if I've got 1 plus a negative 3, that gives me negative 2. Divide that by 2, I get negative 1. Whereas if I drop the negative, I'd get 1 plus 3, giving 4. Dividing that by 2 would give me 2 coulombs of charge. Does that make sense? And for your equation, when you plug your values in, right? So if I've got 1 negative and 1 positive, my final answer will be negative, meaning my force is an attractive force. If your answer is positive, my force is a repulsive force. So I'd always say plug your signs in there, because at the end it reminds you what kind of force you have and what kind of force you're dealing with. Does that make sense? Cool. Is everyone okay with this so far? Okay, let's get into some practice, right? And we'll start off with a very easy one. Let's go straight to like the humdinger of them all. So on page 20, guys, quickly down to page 20. Is everyone there? Give me a quick yay. Yay. Sweet. Now when you're there, take some time. I'll give you guys 2 minutes. Read through that question from the beginning to the very end, and then we'll attempt to answer it now. Okay. Time starts now. Can I erase the board?
Yes.
You guys done reading? Give me a quick yay.
Yes.
Is that everyone? Okay, cool. Let's go about getting the answers for our question. Okay. Okay, now 10.1, they want the current through device X. Yes? So how do I go about that? Hello? What do I have? And? Okay. So, if we remember our power equations, power is equal to I squared R, and power is also equal to V times I. So we have I times R is V, therefore power is equal to I times V or V times I. And what's the other one? Power is equal to V squared over R. Yes? Cool. So now what do I do here? power is equal to V times I, yes. My power is 100 watts. My voltage is 20 volts times I. My current is therefore 50 amps, yes? Wait, sorry, 5. Apologies. 5 amps, yes? Makes sense? Okay. 10.2, find the resistance in device Y. What do I do then? Come again? Do I need to? What's the voltage going through device Y? 20 volts, right? It's in parallel. The voltage will be the same for all the branches. Then for 10.2, I can just find the resistance by using P is equal to V squared over R. Yes? V squared over R. V squared is 20 squared divided by R. My power is 150 watts. And you'll see when you solve that, you should get a value of 2.67 ohms. Quickly here if you agree. Yeah. Sweet. Okay, 10.3, calculate the internal resistance R of my battery. Okay, now we look at the entire circuit. Our EMF is given as 24 volts. Remember, this whole first part is when the switch S2 is closed, right? So that Z resistor isn't in my circuit currently. Yep. So then I need to just basically find the small r of my circuit. So what do I start by doing?
EMF is equal to I, big R plus small r.
Okay. You go up here. So let's solve my equation. EMF is equal to, yes, then what?
Need current.
Okay, what's my current? Do I know my current? Can I find my current?
Yes.
How? Yeah, find the current in Y and then add them all together, right? Okay, so then in, yeah,
No, mine, sorry.
sure. Okay. So now I've got this equation. I've got my EMF. I need my current, and then I've got that. I can solve for that. Sweet. So then the first thing there, I do my equation of power in Y is equal to the current in Y times the voltage in Y. My power is 150 volts. My current is unknown. My voltage is 20. Therefore, my current is 7.5. Yes? 7.5 amps. Now I've got my current. Can I then apply my equation?
Yes.
Okay, cool. So then, going into the equation, EMF is equal to my capital I into R plus small letter r. What's my EMF? 24. What's my current? 7.5. What's my R total?
2.67.
2.67.
Is it from the previous question?
My total resistance for the entire circuit. Yeah, how do I do that? Yeah. Sorry, thanks for that. Actually, we're supposed to add them together. Eh? Sorry. Yes. We're supposed to add them together. So the current in the one above was 5, and this one is 7.5. So my I total, thanks for that, is 5 plus 7.5, which will give us 12.5. Yes? And how do I get my total resistance? The inverse of the?
Two resistors.
Yes. 1 over R total is equal to 1 over R1 plus 1 over R2. Do I need to do that?
No.
Why?
I don't want to get it wrong.
No, just try. The worst that will happen if you get a question wrong is I'll give you the correct answer.
So then you can work out E is equal to I R first,
Okay?
and then that gives you the total R.
Okay, we can do that. Do I need my total R? Yeah?
You have your voltage and you have your I.
Yeah, exactly.
Equals R times I.
Right? Yeah. Because remember, if I take this equation here, this times that is my V external, this times that is my V lost. Right? I've got my V external. Because I only have my 2 resistors, that's the total voltage that comes out of my battery. That's my V external. So I don't even need to find my total R in that case. So what I need to do here is to say, okay, well, EMF is equal to I times IR is V external plus my I times small letter r. This V external is my 20 volts because it's going through the parallel circuit. Does that make sense? You guys sure? Okay. Okay. If we look at our circuit, right? Our circuit looks like this. So we've got our cell. That's a very badly drawn cell. Okay. I'm going to draw a very simplified version of it. Okay. That I'm going to leave out the other part at the bottom. Okay. We've got the voltage here, right? Yes? Which is the same voltage that's there, right? But it's the same voltage that's across my entire parallel circuit. And there's nothing else between my battery and my parallel circuit. Therefore, that is my V external. You guys with me? Yeah. So because there's nothing else, if there was something else here, then you'd have, this would not be a V external. But because there's nothing else here, that potential difference across the parallel circuit has to be the same potential difference across my battery. And therefore, this is my V external. Guys with me? So then that's the value I'm going to plug in here, and then just solve my small r. So then my EMF is 24, my V external is 20, plus my current is this whole thing here, which is 5 plus 7 is 12.5. And my little r is that little r there. And then 24 minus 20 divided by 12.5, we end up with an answer of 0.32 ohms. You guys with me?
Yeah.
If you couldn't see this initially, don't feel bad. Like I said initially, you can still find the resistance of the one, resistance of the other, find your R total, plug it into your equation, and then solve for the small r. This is simply just a quicker way of doing it. Yeah? Hello?
Yes.
Okay, cool. Sweet. And then now we need to find, okay, so now switch 2 is also closed down. The electrical devices still function as rated, and their resistances are unchanged. 10.4, identify the electrical device Z. Well, what could Z be?
A resistor. Meter.
Think of it. I'm connecting another device in parallel, right? But my resistance doesn't change, and everything functions as rated. The power doesn't change. Nothing in that whole circuit changes. What could it be?
A light bulb.
Remember, a light bulb is also like a resistor. It will use up some of my current. It'll change the power being sort of drawn by every other device. It'll change the current being drawn by all other devices. But they said everything remains as is. Nothing has changed by plugging in this device.
Is it a voltmeter?
Yes. So it's a voltmeter, right? So basically what it is, imagine like what I drew here. If I plugged in a voltmeter here, remember voltmeters have incredibly high resistance because you don't want any of the current going through them. So the current's going to get there and think, voltmeter, tons of traffic, not going that way, and then carry on as it was, right? So you're going to have no current going through here, meaning it can and only be voltmeter. Yes? Okay, 10.5. Explain your choice in 10.4 above. Hello?
Negligible resistance.
Not negligible?
All resistances.
No, but not for the voltmeter. Voltmeter's got very high resistance. So because it's got very high resistance, it's going to draw very little current. And therefore, it won't change anything else happening in the circuit. The power drawn by all the other devices will not change. The current of the other devices will not change as well. Okay. You guys happy? You guys happy? Okay, cool. What I want you guys to try out now is on page 19, there's a multiple choice question. And then I want you guys to try the electrostatics question on page 21. Okay, page 19, the multiple choice question, and the electrostatics question on page 21.